Okay? So again, this group work is on probability distributions, which is what we were studying this weekend. Hey, and all you that worked hard on that probability distributions, all you that worked hard on that homework this weekend, I'm telling you, that's what it takes. You want to succeed in an 8-week statistics class, it takes kind of day in, day out work, you know. Now, I'll be honest with you. I have students that'll work 36 hours over the weekend, and I understand when that student comes in and doesn't have homework done, okay? On the other hand, I have students that do that and still get the homework done, okay? I mean, I want you to continue to work hard. You guys are a quarter done with the class, you know? And we're moving into material that's not easy, right? So we got to keep kind of an everyday kind of approach to it. You may find you get behind at times. If you get behind, don't work on old stuff. Work on what we covered today in class and work on that night's homework. You guys should be working only on Chapter 5 stuff right now, okay? The old stuff we'll get back to in due time. But you really want to keep moving in a course like this, okay? So that's something I'm going to recommend. But anyways, I liked some of the stuff that I saw. I think we're getting to understand what a probability distribution looks like, right? You have x values, and you also have probabilities, right? And so, again, we explained where these came from, but I think you guys now have these probabilities, right? So the probabilities are all out of 36. And so, you know, it's funny because in the book, when you guys do the homework, you're not going to have to compute these. They're going to give you the probabilities. You know, we did Chapter 4, we learned how probabilities are computed. This is a more complicated example, I will say that. But once you have the x's and the probabilities, then the question is, what can you do with them? So let me show you one thing we can do with it, right? I mean, first of all, we can answer some key questions. It says, use the table. Can we compute each of the following? Well, what's the first one say? The probability that what happens? Yeah, that you roll a 4, that x is 4, right? Well, that would be, looking up at the chart here, here's x is 4, so it looks to me like the answer to this one is 3 out of 36. Does that make sense to people? Okay. Now for the next one, it says, what's the probability that x is between 6 and 9? Does that make sense to you guys? So to do this one, I would do this. I would say, well, this is equal to the probability that x is 6 plus the probability that x is 7 plus the probability that x is 8 plus the probability that x is 9. And each one of those comes from the chart above, right? So what would the probabilities be we have to add? It looks to me like we have to add 5 out of 36 plus 6 out of 36 plus 5 out of 36 plus 4 out of 36. Somebody asked me, you know, should we simplify? And I guess it's better here that I didn't simplify, because if you add fractions, of course, you need to have a common denominator. And so when you add all these 36 together, what do we get? We get something out of 36. Let's see. 20? You guys got 20 out of 36? Is that more or less than 1/2? More. So more than half the time if I roll 2 dice, I'll get something between 6 and 9. That's what that says. Does that make sense? Okay. How about this last one? X is less than or equal to 11. Well, the long way would be to do like I just did this one, right? But a shorter way would be to use the complement. Do you know what I mean by that? No? We want to do 1, this equals 1 minus the probability. What's the complement of being less than or equal to 11? Yeah, I mean, 2 ways to say it. One is that it's greater than 11, right? You guys see how that's the opposite of less than or equal to? But then what Dylan said is, if you're greater than 11, the only way you can do that is if you have x equaling what? 12. Pull that up where you can see it. Right? So when we're trying to do x is less than or equal to 11, okay, that's 1 minus the probability of x being greater than 11. This is the fast way or the easy way to do it, right? What's the probability that x is 12? It's on the chart. 1 out of 36. Yeah? You guys follow? So final answer would be what? 35 out of 36. Sure, because 1 is 36 out of 36, if you want to rewrite that, right? And so you get 35 out of 36 as the answer to the last one. Okay. So the other thing I asked you guys to do was to compute the expected value of this random variable. And then discuss what your computation means and what it doesn't mean. And this is where I was telling people, well, you may want a third chart, because the formula for expected value is this. The sigma means we're going to be adding up a bunch of stuff. What are we adding? X times the probability that x is x. And so I will want these products, right? We need a new column. X times the probability that x is x. And so you could go right down the line here and multiply these together, right? 2 times 1 out of 36 is 2 out of 36. 3 times 2 out of 36 is 6 out of 36. Right? 4 times 3 out of 36 is 12 out of 36. Here's 20 out of 36. 30 out of 36. 42 out of 36. Let's see, we have 40 out of 36. 36 out of 36. 30 out of 36. 22 out of 36. And 12 out of 36. Can I add all those things together? Sure. The expected value of x is how we write this. By the way, another way we write this, do you remember what symbol we use besides expected value of x? It's this one, the Greek letter mu. What does that stand for? The mean. Somehow the mean is what I'm computing. The mean is a measure of center, right? Somehow the center of this probability distribution is what I'm computing. By the way, how many 36 did you get when you add this all up? What'd you get? 252. Does that reduce to what? It's exactly 7. That's what we computed. When you roll 2 dice, the expected value of the sum of those dice, or maybe a better way to say it, the mean of the sum of those dice is 7. See, here's what I don't want you to think. Does this mean I expect to roll a 7? No, that's not what it means. Like, actually, what's the probability that I'll roll a 7? We already have that. It's only 1 out of 6. You probably won't roll a 7, right? Even though it's the most likely thing to come up, you're probably not going to roll it. 1 out of 6 is the probability, right? But when I say that's the expected value, what that's really telling you is that somehow that's the average roll. If you roll dice many, 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 many times, and if you graph the distribution, and I know that we did this with you guys on the machine, you get this kind of look where the center of the distribution is right there at 7. Does that make sense? Now, by the way, you can also compute the standard deviation of a probability distribution. What does standard deviation tell me? It doesn't tell me the center. It tells me what about the probabilities? The distance from that 7. Yeah, how far apart they are. And I'm not going to do that now, because I don't want the focus to be how to compute. We have calculators and computers for that. I want the focus to be on understanding so that when I write down mean, you guys understand that's the center. And when I write down standard deviation, that's how much spread out it is. Comes right down to it, guys. You're not going to be doing a whole lot of computation in life, I don't think. But you will have to interpret, and that's kind of the point of the course. You know? So that's where I'm at with this one. We did homework this weekend on probability distributions, and someone asked me to go over number 25. I think it was Dylan. So I'd like to do that. If we can go to the book and look at it. So what page was this one on? Is this it? Can you guys see it, or should I turn it up a little bit, Amy? Okay. Let's get a little bit bigger. Oh yeah, expected value in roulette. You guys know the game roulette? You have a wheel that gets spun. How many have seen a roulette wheel? Not everybody. Let me show you. I'm sure a quick Google image, right? We could take care of this. Let's look. You guys have computers. I should really make you do it, but let's see what we come up with. Roulette. Come on, roulette. Show me images. Well, okay. So there's this wheel, right? Here it is. And you spin the wheel, and see that white ball there? That ball is going to land somewhere on some number. And people place bets down on what number is going to come up. You don't have to do that, though. You can just bet what color is going to come up. You can bet even or I mean, hey guys in Las Vegas, if you want to bet, they're gonna let you bet. That's how they make money, right? Because there's ways of winning and ways of losing. By the way, suppose you decide you want to bet black. You'll notice that it's almost true that half the numbers are black, and so you'll win whatever you bet. If you win, it's a 1-to-1 payoff, you could say. And if you bet red, same thing. So why did they pay off what you bet if it's only a 50-50 chance? Well, the thing is that the house has an advantage because there's, do you guys see the other number there?
There's a 0 and a 0.
Yeah, they're in green. Do you see the green number? That's what makes the probabilities get thrown off just enough that the house, in the long run, is, they're going to lose money sometimes to people that are lucky. They're going to win money sometimes, but that's what throws things off. Okay? Anyways, this problem about roulette wheel, let's take a look at it and see if we can understand what it's asking and go from there. Because this was, that's not it. Where'd it go? Oh, I think I
think it's the first one.
oh, there it is. Thanks. Okay, a gambler's trying to decide whether the $5 on the number 27 or bet $5. Okay, so here's, from example 8, we know the expected value of the $5 bet for a single number is negative 26 cents. Hey Dylan, did you look at that example 8 or no?
Yeah.
Yeah? So you understand that?
Kind of.
Kind of? Okay, so let's look at the example, because I know that there's plenty of people that didn't get a chance to look at this yet. So is it okay if I just go there first? All right. So example 8 was back a few pages. Do you guys have it? I'll just get to it. In due time here. Is this one it? I think. Here's some betting. Is that it? Yeah, here's the roulette wheel. Right. Okay. So the probabilities and payoffs for betting $5 on the number 7 are listed. So if I go back one more page, I think it'll help. Okay. So they're talking about, yeah, that's not that. Here we go. So they want to talk, oh, I see. So they want to talk about which is the better bet in example 8 here of roulette versus craps. I don't want to do that with you, but I do want to talk roulette. So, okay, what you need, guys, is you need to know this. Otherwise, we can't really do it. If you bet $5 on a single number, the probability of losing that is 37 out of 38, and the probability of making a net gain of $175 is 1 out of 38. It says the prize is $180, including your $5 bet. So the net gain is $175. Find your expected value if you bet $5 on the number 7 in roulette. And they show the work here, okay? So basically, if you want to compute expected value, you want to list kind of all the possibilities and what the probabilities are. This is a frequency distribution, right? This is a lot like what we just did with 2 dice. But the difference is that they kind of lumped everything together. They said, well, you're either going to win or you're going to lose. And these are what they have, okay? And maybe going through the one here would make more sense. We can compute it. So they say you're either going to lose $5, and that's the probability, right? Why do they get that 37 out of 38? Well, the numbers on a roulette wheel are 1 to 36, 0, and 00. And if you bet on the number 7, the only way you win is if that 7 comes up, right? So the chances of winning are only 1 out of 38. Does that make sense? So you have the probabilities. You have the payoff. They said you'll win $180 if you win, but you bet 5, so it's really only $175. So you either lose 5 or you gain $175. They multiplied. When you multiply 5 times 37 over 38, you get this decimal, but we have to put a negative in front of it because that's losing. So you expect, the expected value of loss here is 26 cents if you round it. Okay, so we're going to try and do the same thing in problem 25 with a different bet. So here we go. One more page. They say, part A, find the expected value for your $5 bet if the outcome is 0, 00, 1, 2, or 3. Okay? So it's weird because you put your coins down, and if any of those 5 come up, you're a winner. The other option is you lose, right? So let's write this down, guys. You have paper? Let's make a chart, kind of like they did at the beginning there. We're going to write win or lose.
I don't know if some casinos let you bet on 0 or 0.
What'd you say?
I don't know if some casinos let you bet on 0 or 0.
I'm not talking about casinos right now because I don't know the rules, but we're saying in this problem that you are allowed to bet this 0, 00, what were the other ones? 1, 2, 3? Yeah, 1, 2, 3 bet. So again, this is problem 25 from section 5.2. And so this bet, what can happen? If one of those come up, you win. If none of those come up, you lose. Now, X is going to be how much you win. If you lose, by the way, that's easy. I know how much I lose. I lose $5 because I could lose. That's what I'm betting. I'm betting in dollars, right? These are dollars. How much do I win? I think they said. Does it say? Well, $30. There's a 5 out of 38 chance of making a net profit of $30. Now it's interesting. I guess what you win is you win 35. When it says net profit, that means they took out the $5. So I'm either going to win $30 or lose 5. Here's the probabilities. Right? What are the probabilities? Well, since there's 5 numbers, it turns out that there's a 5 out of 38 chance of winning. What's your chances of losing then? That's easy enough. Right? 33 out of 38. Does that make sense? Okay. So again, that rule of complements comes up all the time in probability. So now I need to multiply, right? So we're going to have 150 out of 38 when I multiply 30 times 5. Right? Whereas your probability of losing is 33 out of 38. So when I multiply, again, we have to do x times the probability of x equaling x, right? When I multiply these two together, what do I get? Yep. It's 165, but then we're going to put what? A negative, because a negative times a positive is a negative. So I have negative 165 out of 38. And so now when you add those, okay, the sum of the x times the probabilities would be positive or negative? Negative 15 out of 38. Let me get a decimal value of that. If we do negative 15 out of 38, and I need my calculator to get that, unless you guys help me out, please. What do you have? 0.39? So it's negative 0.39. Okay? So this is the expected value. Negative 0.39. Great. All right, so now the next part of the question, question B. Which bet is better? A $5 bet on the number 27 or a $5 bet that the outcome is one of these three, and why? And again, I'll do the 15 out of 38 real quick. Well, we already got that. Question is, which bet is better and why? Remember, if you just bet on 27, we said that the expected value, what did they say? Well, let's make sure. I know it's negative. Negative, let's put it back up. 0.26, right? You're going to lose 26 cents? Is that what it means? Now, that's not going to happen, guys. You're not going to lose 26 cents. But what this is saying is, if you play over and over and over again, guess what, guys? Either kind of bet, if you do it over and over and over again, you know what's going to happen in the long run? You're going to lose money. On the average, every time you take a bet, you would lose 26 cents if you bet on 27. On the average, every time you make a bet, you would lose 39 cents if you do this bet. So which is a better bet, you might say? Yeah, just bet on a single number, you could say, is safer in a way, or a better bet. Well, what does it really mean? I mean, it really means if you want to make money, don't do it by going to a casino, right? That's not a way to make a living. But you know who's interested in calculations like expected value? Insurance companies. Sure, actuary is the mathematical title, but why do insurance companies, how do they work, right? Well, you have auto insurance. Millions and millions of people are paying a rate, right? It's required. It's law. You have to have an auto insurance. And somebody gets in an accident, then the insurance company pays out, right? But how do they know what to charge? Well, they look at the probabilities of getting in an accident. And they look at how much money they'll have to pay if someone gets in an accident. And that helps them figure out what to charge the rates. But they always make sure, whatever they charge, they have to make sure that the expected value for them is positive or is negative for the drivers, so that they can make some money. Does that make sense to you guys? Does that mean you can't win big on a casino? No, you can, right? But it means in the long run, when many, many, many people play, and the casino is the one that plays many, many times, they know in the long run, on the average, people are going to lose. Does that make sense? So that's expected value. Cool. We're going to talk now about a particular type of distribution called a binomial probability distribution. This is 5-3. So here I go. And let's go through a little here. I'm going to talk first of all about what's called a binomial random variable. Okay? So these are used for counting the number of successes. And I put that in quotes because what does that even mean? And part of your challenge is going to be to understand what we mean by success. Okay? And then we're going to have to, it's going to be after a situation where we know the probability of success for one trial, let's say. Okay? So I'm going to give you some information on paper. I want you to put the pencil down for 1 second here and just watch this slide. This is what is the binomial probability formula. But I want to write this down for you in a clearer way. This is what the book gives you. But do you guys recognize that fraction thing at the beginning? You should. What is that? Yeah, it's one of those ones we just had from chapter 4. Do you guys know which one? Is this permutations or is this combinations? Maybe we don't know the formulas that well. This one's combinations? How do you know? Yeah, I mean, it has, see how it has x factorial and it has n minus x factorial on the bottom? All this formula is the combinations, that first fraction. And I think your book doesn't really talk about that very much. So I want to go over this, but in my own way. And I want to do it in context. So here's my problem, guys. Ready? Maybe we have an election coming up in our state. Actually, I have an election coming up in my city. Shaker Heights right now is trying to approve a school levy. Okay? Suppose that 65% of the people, say in Shaker Heights, are opposed to a school levy, and then the others favor it. So here's what you might do. You might say, I'm going to survey 7 people and see what they think. Right? So I call up 7 people. And the question is, what is the probability that a majority of them are going to support the issue? See, this can be a problem. In real life, in this example, do people in the state support the issue or oppose the issue? What's that say? 65% what? Oppose it. But I can't call everybody to find this out. So what do? I call some of them. Suppose I call 7 people. Do you think my 7 people I call, I might think that people support the issue? Depends what happens, right? Could it be you could call all 7 and they all support the issue? Could be. There's a lot of people in the state, right? It kind of depends who you call. So I want to show you kind of how we tackle a problem like this one, because this is what's going to be called a binomial distribution problem. Here, watch. So, here's what you need to know. We'll say capital X is a binomial random variable if it counts the number of and I'll put it in quotes again, successes, and maybe I'll say in parentheses, opposite of failures. I better put this where you can see it a little bit better. Okay? And I'm going to list now the different pieces of the formula. Okay? In the formula, little p is going to be the probability of a success. By the way, I guess we have to decide what we want to call success in my problem I'm doing. Oh yeah, I asked you guys, so in my example, here I'll do it down here. In my example, we survey 7 people, and the question was, what is the probability that the majority are in favor of the issue? Oh, and I had one more fact. Do you remember what the percentage was of people in the state that... Well, I guess I didn't say how many were in favor. What did I tell you? I told you 65% in the state oppose, right? So, what percent are in favor? Okay, 35% are in favor, we're going to say. Does that make sense? Okay. So I'm going to say in our example, little p is equal to 0.6, no. Little p, let's say in favor, right? So little p, let's make that equal to 0.35. 0.35. Okay? There's going to be another variable in the formula called little q. Little q. Little q is the probability of failure. And so, by the way, automatically, q is equal to 1 minus p. Does that make sense? So in our example, what does q equal? 65%. Okay. So these are always, p and q always add up to 1. That's kind of the point. N is the number of times we repeat our experiment. Now it's funny because that makes it sound scientific, right? Number of times you repeat your experiment. The experiment this time is I'm going to make a phone call, guys. I'm going to call somebody. How many times am I going to make a phone call in this problem? 7. So n is 7. Okay? So now I'm going to write down the binomial formula, okay, in the following way. The probability, maybe I'll just put it right here in a big box. Let's do it in green. The probability that capital X equals, and do I want to use X or K? I'm going to use little x, is equal to, I'm going to write this first, n choose x, n choose x, times little p to the x power times little q to the n minus x power. This is the binomial distribution formula right here. So let's show you how the formula works. The probability that x equals x. So my question was, what's the probability that the majority of the people I call are in favor of the issue? Now we say majority. How many people do I need to have a majority? Okay, so in my example, how many? I'm going to make a phone call. That person's in favor. I make another phone call. That person's opposed, right? Right now it's 1-to-1. I'm making 7 phone calls altogether. So if I ask you, what's the probability of it being a majority, what would you say?
4.
I'm going to say 4, right? Guys, skip some space and let's use this formula, but let's skip some space and down here somewhere, I want to compute the probability that x is 4. I'm going to show you guys how to do that. Okay? Actually, I have that calculator up there, don't I? Yeah, I might use that in just a second here. So here I go. The probability that x is 4, according to my formula, is going to be, see how it says n choose x, little x? That's going to, what's n again for us? 7 choose 4, because we're computing the probability that x is 4. Does that make sense? Times what? Well, we need p, and little p is 0.35. To what power? No, we need to the x power 4. This is where you got to kind of keep straight what's what, and that's why I'm trying to do this carefully, right? Times 0.65, because that's what q is, and it says to the n minus x power. What's n minus x? 7 minus 4 is 3. So these two numbers always have to add up to n, right? And so if I could compute that probability, that'll tell me the probability that x is 4. So I go to, say, the calculator. Again, we can do this with calculator or computer. I'll show you guys calculator first. Okay? So how do I do? Well, you guys know how to do this part, right? 7 choose 4. I hit 7 and then what? Math. Go over to probability. We've done this. Please work for me. There it is. And then what choice do we want? Choice 3, right? 7 choose 4. Okay, I got that. Hit the right arrow. That'll get you back up here. Now I hit the times button. Times what? Well, we need 0.35. And now we need an exponent. Do you guys know how to get that?
You made a negative.
What's that? Oh, I made a negative instead of a point. Thank you. We don't want that. Yeah, this should be 0.35. So 0.35, how do I get an exponent? This caret key above divide, right? To what power? The 4th, okay? And then times again, and we have 0.65, and we need the exponent, and this would be to the 3rd power, right? Enter. So it says 14%, 0.1442 I'm going to write. That's this. 0.1442. That says there's a 14% chance when you call, you might get the wrong information. You might think, well, no. That's the probability that 4 people are going to say they're in favor of the issue. The school levy or whatever it is. But wait a minute, guys. There's other ways to get a majority. Right? This is only part of the answer. I said majority. What if you call and 5 people say they support the issue? Is that possible? Is it as likely? Well, we'll see. Probably not, right? Now take a look. How would we compute it? It's almost the same formula, right? It's going to be 7 choose what? 5 times 0.35 to the what? To the 5th power this time, because we're saying, what's the probability of x equaling 5? And then we also have to multiply by what? 0.65 to what power? To the 2nd power. That's right, Russell, because we have to, these guys always have to add up to whatever n is. Does that make sense to you guys? No? Yeah? Okay, so let me show you a nice shortcut on your calculator. I love shortcuts for the calculator. So one thing you can do, if you have something that you just typed and you want to get it back and just modify it, here's what you do. You hit the blue button, second, and hit enter. And look, I get right back what I had. And now I can just kind of go through and make my changes. So over here where it says 7 choose, I'm going to make that 7 choose 5, right? And then I'll come over here and make it 0.35 to the 5th power. And then I'm going to come over here and make it 0.65 to the what? 2nd power. And here we go. There is almost a 5% chance of that happening, right? It's 0.0466. So you guys, the answer to this question that I posed, what's the probability that a majority support? It's more than 14%, right? I mean, we just calculated this other piece, 0.0466. All right, already we're at 19% if you just add those two together. You with me? But I'm not done yet, right? What else do I have to compute? I have to compute the probability that maybe x is what? 6. And I also have to compute maybe you call all 7 and they all say they're in favor. But really we know that 65% of the people oppose, but it might be you start calling people around the state and you happen to get 7, right? That could happen. So this is a way of computing those probabilities. Are you with me? Here, let's find out. Could you guys try to compute the probability that x is 6 and the probability that x is 7, and then we'll have it? Use the calculator and do that. So let's see here. I guess I can do this pretty quickly. Probability of x equaling 6. Change that to a 6. Change this to a 1. And I'm getting, anyone else get that? 0.0083? I think, okay, you got it? Good. If you're getting 0.0083, then you have that part right. Okay. 0.0083. Now the last piece of this, right? It turns out, you guys, what this 0.65, if I do it again, is going to be raised to what power? Do you know what anything to the 0 power is? It's 1. So you can kind of ignore that piece. We're also going to have 7 choose 0. There's only one way of choosing 0. So really, the whole answer, what's the probability of getting 7 that all are in favor? It's just going to be 0.35 caret 7. Enter. What's that mean? That's 0.0006, right? So 0.0006. There we go. So if you add these all up, okay, I can now answer the question. This adds up to about 0.20. So what's the probability that a majority will be in favor of the issue? That's about 20%. There's about a 20% chance when you make your phone call, you're going to think that a majority support the issue. Okay? Hey, tell you kind of where we're at this point, because I'm going to stop because we're out of time.